So up next is Jacksen Narvaez, student at the Royal University of Berlin. We're talking about magnetohydrodynamic simulations of accretion disks. Please go ahead.
Yep. Hi, everyone. Sorry for the problems. Okay. Yep. I'm Jacksen. I'm a master's student at Memorial University in Poland, currently working under the supervision of Dr. Terence Trico. Our project is about magnetohydrodynamic simulations of accretion disk. I have to mention that I just finished my first term, so I haven't worked for a long time in this project, but we'd like to show you like the first steps and results and some challenges that we are facing. So what a better place than the Phantom workshop to do that. So just first, we know that accretion is like one of the main factors to determine the evolution of accretion disk, like in protoplanetary disk. And for that, we need to have mechanisms to transport angular momentum. We know that molecular viscosity is very inefficient to do that. So it's here that back in 1973, Sakuran and Jai proposed the famous pseudo-viscosity that is related to the turbulence of the disk. Nowadays, we express this pseudo-viscosity as proportional to the speed of sound and the height scale of the disk. And this famous alpha parameter that basically tells us about the efficiency to transport angular momentum. It's related to the turbulence. And well, it's here that magnetorotational instability is one of the main mechanisms to generate the turbulence in the disk. This is because of the few requirements that it needs to arise in the disk. In the case of ideal MHD, we only need of angular velocity that decreases with the radius. Here I show you a simplified sketch of how MRI works. We assume an uniform vertical magnetic field, and we take two elements in the same radius. And we include a small radial perturbation such that one of the elements is closer to the central start and the other one is farther away. So as the rotation, it's a function of the radius, we have that the inner element will rotate slower than the fluid, opposite to the outer element. And so the inner element will lose angular momentum and will continue falling down to the central start, opposite to the outer element. If the magnetic tension is not strong enough, so the two elements will separate, and that's the origin of the instability. So regarding numerical simulations, we have global disk simulations previously that mainly use grid codes, like for example, Pluto, Athena, and Global, and Nirvana. But regarding meshless codes, we only have local simulations that use the shearing-box approximation. In this case, we only simulate a local parcel of the fluid. And we have identified that the main challenges for the meshless codes to simulate global MRI simulations, it's first the resolution, the dissipation, and the divergence-free constraint. So based on that, the main objective of our study is to evaluate the suitability of the Smoothed Particle Magnetohydrodynamic algorithm to reproduce MRI in global disk simulations. This is the model setup that we use. We only assume a gas disk with ideal MHD. For the initial conditions, we consider disk with 5% the mass of the central star. The disk is thin, and we assume at the beginning there is a hydrostatic equilibrium. So these are the surface density. This is the angular velocity. So far, we have assumed only purely toroidal magnetic fields that we calculate the strength of the field based on this famous plasma theta parameter. And we assume for the equation of state and locally isothermal equation of state in this way. So this is the setup for Phantom. Initially, we consider the radius from 1 to 10 code units. And we use resolutions greater than 1 million particles. So far, we have used 3 resolutions, 1, 2, and 4 million particles. We use Phantom for the simulation and for visualization, the Saracen code. But also, we want to compare these results with mesh codes because they have produced previously MRI successfully. So for that, we use the Pluto code, which implements the Gotunov scan. Here the domain goes, it went from 1 to 8 code units, and we simulate only a quarter of the disk. That is, phi goes from 0 to 90 degrees. We use more than 100 million cells that I would try to set those cells as close as possible to a qubit cell, as you see here. And yeah, for the simulation, we use the Pluto code, and for visualization, we use the PyPluto library. So how well do we capture MRI based on those resolutions? For that, we use this parameter, the wavelength of the fastest growing mode of MRI, which is proportional to the ratio between the alpha velocity and the angular velocity. Based on previous simulations, we know that the ratio of that wavelength and the characteristic size of the cell has to be greater than 5. In our case, we have values greater than 20, between 20 and 34. So that means we have good resolutions there. And for SPH, well, there are not many works there to compare with. So we took from local simulations this quality factor, the wavelength of the MRI growing mode, and H is the smoothing length of each particle. And as you see here in the simulation of 1 million particles, that value goes between 2 and 10. So that's one of the problems that we are facing now, the resolution. And yeah, so here is the early disk evolution based on the Pluto simulation. We observed that in general, the disk, the fluid becomes unstable around 10 local orbits. Here, the time is given in orbits at a radius equal to 10. And yeah, so far we have been able to simulate this disk until 3.5 outer orbits because the resolution is still running. So yeah, we need to wait for more results to be generated. But let's wait for the simulations. Okay, we observe that in general regions upper and lower than around 3 height scales, there the plasma beta parameter becomes lower than unity. That means that the magnetic pressure becomes important in those regions. And one of the most important results or characteristic results of MRI simulations is the butterfly diagram. Here we have the azimuthally averaged toroidal magnetic field and the evolution in time. So we have this like change of orientation in the magnetic field. This is a simulation of from Flocketel 2011. And here are our results. This is the toroidal magnetic field, and this is the radial magnetic field, which is around 1 order smaller than the toroidal magnetic field. But we clearly observe here the changes of orientation in the toroidal field. So so far we have got good results in that with Pluto. And what about Phantom? Well, this is like a characteristic simulations among all the runs that we have implemented so far. Here I showed you the magnetic energy density. Here is the toroidal magnetic field. And at the beginning, we observed this growth of strong toroidal fields that we thought, okay, this could be because of the activation of MRI. So we decided to improve the divergence cleaning of the magnetic field. We do that based on the method of Trigo et al. 2016. So we improve the divergence cleaning, and we observed that we solved that problem with the strong toroidal magnetic fields. Okay. And so we tried to change different parameters, the resolution, the kernel, and the artificial resistivity that we use in the simulations. Here I use different resolutions for an overcleaning parameter, which determines the efficiency of the divergence cleaning of the magnetic field equal to 20. We observe that there is not much difference between the evolution of the magnetic energy for the 3 resolutions, 1, 2, and 4 million particles. The lower flow is the error of the divergence cleaning. But we observe that there is a huge difference between the value of the overcleaning parameter. Here is the value by default in phantom, the value is given to 1. If we improve this to 20, we observe that the difference for 1 million particles is very evident. So yeah, with that, we prove that divergence cleaning is a crucial factor in the evolution of magnetized disk. We tried also with different kernels. Here I tried with the cubic, the quintic, the C4 and C6 Wendland kernels. And we observed that for the case of the quintic and the Wendland kernels, there is a point around 3 outer orbits that the magnetic energy decreases by several orders of magnitude. So the magnetic energy is being dissipated from the system. We don't know exactly why. We are evaluating the terms of dissipation of the simulation. And based on previous local simulations, we also try to reduce the artificial resistivity in the system. So that is set by this alpha B parameter. By default in phantom, phantom uses a value equal to 1. So we tried with a value equal to 0.3. And you observe here at the beginning, there is a growth of the magnetic field. But again, after like 3 outer orbits, same result, the magnetic energy is being dissipated from the system by several orders of magnitude. So, yep, the same result like for all the simulations. We observed that after around 3 outer orbits, the magnetic fields vanishes, sometimes by several orders of magnitude. Also, in like most of our simulations, we observe here in the center, there is a change of orientation of the toroidal magnetic field. We need to evaluate that further to see if this is like related to the MRI activation or it's just a numerical error. So yep, here is the summary. How many time do I have? Okay. So yeah, here is the summary. So far, sadly, we haven't been able to activate the MRI. We found these critical problems, the dissipation of the magnetic energy, the divergence cleaning. So as future work, we plan to evaluate how that energy is being dissipated, for example, by artificial resistivity or divergence cleaning, and also improve the resolution. But as you see here in this plot for 4 million particles, this is the quality factor. We need to improve that resolution mainly here in the inner region of the disk, where the quality factor becomes lower than 5. So based on the adaptive particle refinement, it will be better that, for example, if we improve the resolution up to 10 million particles, that we allocate those particles in the inner region, such that we improve the resolution in the disk. So yeah, that's all. Thanks so much for your attention.
Very nice work. Just to comment on the kernels blocks. So these are the different neighbor numbers. And so if your result is very sensitive to resolution, change the kernels and each kernel acts its sort of favored neighbor number. These are not the same resolution. You're not comparing, and so the Wendland's uncertainty 40 would be at lower resolution, and that might explain some of it. If the problem is very resolution dependent, that would explain.
Yeah, exactly. I mean, that justifies the results for the Wendland kernels, but not for the case of the quintic. Sorry, the quintic kernel.
The same would happen with the quintic as well, because if you use it must be different neighbor numbers than the cubic, because if you use them the same as the cubic, it would just be a very bad density estimate.
Oh.
So each kernel by default would maybe number that's optimized for it. I think that's how it works in Jacksen.
Yeah.
And that by default would mean it's a different resolution. The same number of particles, they're all 1 million particles, but they have very different resolution.
Yeah. Yeah, I see the point. Okay, thanks.
Daniel.
Just wondering, maybe it's more fun to try. I mean, there's a lot of things in Pluto using 100 million cells, using a log radius grid, and you have different boundary conditions. So like, I wonder if you might be easier to change some of those things. Like if you use a linear grid, if you use 1 million grid cells, if you try to make something like the free boundary condition that you have, are things different? Maybe you can come at it from that angle.
Yeah, well, so far I have tried with 3 different boundary conditions, but similar results. But in the other side, when I try with lower resolutions, yeah, there are some times that I don't observe the generation of turbulence.
In Pluto.
Yeah,
right.
Exactly. So yeah, in general, resolution is a problem for all the codes, but I think especially in like SPH maybe.
I should talk to Timothy.
Oh, any other quick question? Otherwise, we'll head to lunch. All right, let's thank Jacksen again.
I mean, what is the status of MHD?
She's testing.
Is this something that could be tried in one test or not?
Yeah, probably. I mean, for MRI, it's probably about 50 particles per scalar that you need to get something. So it should be in the neighborhood of 250 million particles, something like that. We can do it.
Cool.
So we're breaking for I think an hour and 20 minutes. We're coming back down to 1:50. But do not trust that clock.
Sure.
Right,
Okay. Ah, ok.